Hey, I'm Amanda Olson, and this is section 5.7, homework problem number 17. In this problem, we're asked to find any relative extrema of the following function, and this function deals with the inverse tangent functions, otherwise known as arctangent functions. So in order to find extrema in a calculus setting, the first thing we want to do is find critical values. We're not guaranteed any extrema for this function because we don't have a restricted function. We don't have, it's not continuous on a closed domain. So we aren't guaranteed, but probably, we can expect some extrema. So to find extrema, we want to go ahead and first just look at the derivative and find those critical values. That will help us to locate extrema. So then for this, we need to find the derivative of the arctangent function. We need that. So if you have it memorized, that's good. If you don't, then you can, reference a formula sheet. You won't be given a formula sheet on the exam, but you'll be able to at least kind of look at it. So the derivative of the arctangent of x is just going to be 1 over 1 plus x squared, and then minus the derivative of arctangent of x minus 1, since x minus 1 is a function of x. It's going to be almost similar, but we need to apply the chain rule. Luckily, though, the derivative of arctangent of x minus 1 is just 1 when differentiated with respect to x. So then we have 1 in the numerator, 1 plus x minus 1 quantity squared in the denominator. And then we want to figure out, so we've got the derivative, we can probably simplify it, and then we want to look at where's that derivative undefined, or for what values is it equal to 0. So just to kind of simplify some things, I'm going to go ahead and combine these two radicals into a single rational expression. I guess we don't have to do that, but I'm going to recursively FOIL or recursively distribute the denominator. Then we have x squared minus 2x plus 2. So we'd want factors of 2 that add up to -2 in order for that to factor. And it doesn't need to. My goal would just be to combine these to be a single rational expression. So what I am going to do is I'm going to consider, well, let's look at where is this derivative equal to 0. So f prime of x equals 0 if and only if this 1 minus 1 over x squared plus 1 minus 1 over x squared minus 2x plus 2, if that equals 0. Because we don't need to combine it. I know originally I was going to start combining them to a single rational expression, but then I realized there's not really going to be anything that factors or simplifies. So for right now, I'm just going to stop and look at where does this derivative equal 0? For what values of x does the derivative equal 0? And so when we do that, we end up with 1 over x squared plus 1 equals 1 over x squared minus 2x plus 2. And then using the cross product property, this is going to happen when x squared minus 2x plus 2 equals x squared plus 1 times 1. So both of those, we just use the cross product property since we have a proportion. From there, we can go and subtract x squared from both sides. And then we can also subtract 1 from both sides. Okay. When we do that, we are left with the x squareds on the left and the right. Both cancel. We have negative 2x plus 1 equals 0. So then we have 1 equals 2x, or x equals 1/2. So for that value, we know that the derivative will equal 0. So we can use the second derivative test then to see, is that going to be an absolute min or an absolute max, or a relative min or relative max, excuse me. Second derivative tells us about the concavity, so we can see, do we have that hill or do we have that valley at that 1/2 point? So we've got that. The other thing to consider is, where's the derivative undefined? Is there anywhere where the derivative is undefined? Well, the derivative is going to be undefined when that denominator equals 0 for an x value that makes the denominator equal to 0. Because x squared plus 1, if you think about that, its output is always going to be a minimum of 1 or larger. X squared is always positive, and you're adding it to 1. So you're never going to get 0. So that doesn't equal 0 for all x. And then if we look at the x squared minus 2x plus 2, let's consider, where does that equal 0 anywhere? Well, the vertex, let's look at where that vertex. We can graph this, or we can consider what does the graph look like? Where does this equal 0? We could try and solve it. We did see, though, if we set this equal to 0, it doesn't factor, so it doesn't have like a nice solution, but we can consider, well, what is the square root of negative 2 squared minus 4ac? But when we do that, we get a complex solution. So based on that, we can determine, this is going to be, because we're going to have a square root of negative 4. And that has imaginary solutions. So basically what we can consume, this also does not equal 0 for all x in the reals. Okay, so we know this derivative is defined over all the values that we've considered, because that denominator never equals 0. The only place that the derivative as a whole equals 0 is when x equals 1/2. So we just want to go then and check, well, what happens at x equals 1/2? Is it concave up or concave down? And so to do that, I'm going to use the second derivative test. You don't have to use the second derivative test. You can use whatever test you like, but I'm going to try the second derivative test. So f double prime, I'm going to take f prime and then differentiate. So you can use the quotient rules. It's not really a nice one, no matter how you look at it, but the quotient rule for the first term, we have times 0. You could also use the chain rule for that first term. And then minus. And I'm going to use this version, the x squared minus 2x plus 2, to differentiate. But again, we have that first term, we have that x squared minus 2x plus 2, but then times 0, we know that's going to cancel out. And then the denominator, we have x squared minus 2x. So we have minus 1, 2x minus 2 for that numerator altogether over x squared minus 2x plus 2 quantity squared in the numerator. So f double prime of x, if I kind of simplify, we have a negative 2x over 1 plus x squared squared. And then we have a plus that negative times that negative. We get a plus 2x minus 2 in the numerator. And then we have that x squared minus 2x plus 2 squared. Okay, so one of the things with this is that is a fraction. If we had a single rational expression for a second derivative, that might have been a place where finding that combining the first derivative into a single rational expression might have been helpful, because then our second derivative really would be a single rational expression. So we would be in good shape. However, we didn't do that. The reason that would be nice is because you'd have a single quotient, you'd have a single numerator, a single denominator, and you could see, what's the sign of each of those to determine the sign of the second derivative. We really only have one value that we're testing though, so I don't know that that's like a huge thing for us. So the denominator though, that is always going to be positive. So we see that, but let's go ahead and look at this numerator. So this as a whole, if I consider f double prime of 1/2, well, this numerator is going to be negative for 1/2, and this denominator is going to be positive. And then we're dealing with 1/2 times 2, which is 1 minus 2. We have a negative here over, again, that denominator is going to be positive. So we're combining, negative plus a negative. So f double prime, kind of doing some waving my hands. You can find if you feel like doing the arithmetic to actually work it out, you can do that. But we can see that it's going to be less than 0. F double prime is going to be less than 0 or less than or equal to 0. So what that tells me then is, if the second derivative is less than 0, I always say that makes a frowny face. It's negative and it's then a frowny face. So it's concave downward. And so if it's concave downward, though, what we see graphically is a hill. And so we can then say that f of 1/2 is a relative max. What is the specific relative maximum value? Then we'd want to plug it back into our original function. So f of 1/2 is going to equal the arctangent of 1/2. And then 1/2 minus, we're going to have minus the arctangent of a negative 1/2. All right, and we want to just go ahead and I have the unit circle that I like to use. You can use the unit circle. You do have the unit circle on the test. Otherwise, if you have a calculator as well, you may use that. I think that, let's check out what the arctangent. Yeah, so it definitely doesn't like the negative 1/2 in the arctangent function. but we should get about 1.096. So we have, well, this is for strictly just 1/2, and then we have like a 1 point, depending on where we round it, and it says to round to 3 decimal places, so 1.093. You plug that in. So, all right. Okay. Thank you.